let's look at more closely the absolute value function. Now you may remember the absolute value function looks like this. Basically it looks like the v, and where its point is at the origin right here. Now there's a reason why this happens, and it has to do with the fact that the equation for the absolute value function is absolute value of x. Now let's remember, when you have the absolute value, we're talking about the distance from 0. And remember, absolute values always turn your values positive because distance is positive. So what's really cool about the absolute value function is, if you can imagine, if you actually take the identity function, which would be in quadrant 1 and then quadrant 3, right? If you take this piece and you make all those negative outputs positive, then you ultimately create the absolute value function, which is kind of a cool idea. And what's really neat is that if you remember what the identity function is, essentially you can make the absolute value function. Now, I must share with you that the absolute value function can be thought of as a piecewise function. So let me show you what that looks like. So if you create a separate function and you divide this up from all the values greater than or equal to 0 and everything less than 0, you can actually make two pieces. So let's think about this. If I'm looking at all the values at 0 and to the right, I'm on this piece right here. Well, that piece is the identity function itself. So we would say x. Now, what happens though if I look at the piece on the left here? Well, it's almost as if it's a reflection, if you can imagine this, of the identity function. Well, what would that equation be? We know the identity function, remember, is y equals x. So if I were to reflect that over the y-axis, I would get y equals negative x. So you can think of the absolute value function as a piecewise function divided at 0. And the actual value of 0 can actually exist on either piece. I just went ahead and put it on the piece to the right side of 0. In other words, the positive side to the right of 0. But this is another way that the absolute value function can be expressed. So it's important that you see that. Now let's actually analyze this a little bit more. So let's talk domain. The domain of the absolute value function is, in fact, all real numbers. There is anything you can put. There's no restrictions. You can put anything you want in there. Next, let's talk range. Let's look at the outputs here. Well, I know the range cannot be all real numbers because no part of the graph actually exists below the x-axis. So no, I know I'm capped to only above it. So I know it's going to be at least to positive infinity in terms of my upper bound. The question, though, is what's the lower bound? Well, I can see that the base of the graph here stops at the origin, and it does actually equal 0. It does give me an output of 0, as I can see right here. So I can actually include my 0 value there. Now let's look at intercepts. Like in our identity function, this does go through the origin, which means both the x and y-intercept are the same. They're exactly the same. For the absolute value function, what we can see here is it does have even symmetry. Also, what this graph does is it decreases and then increases. So we can say on the interval it is decreasing. That would be from negative infinity to 0. And then it is increasing from 0 to positive infinity. Now, I'm not actually including 0 in either of those values, and that gets into some later ideas of what it means, what actually happens at 0 and differentiation and derivatives and so forth. So I want you to know that to the left of 0, the function decreases, and to the right of 0, the function increases. So this is your absolute value function.